A demolition incident involving a 277-volt lighting circuit resulted in the tripping of both a 20-amp branch breaker and a 400-amp main breaker. Several factors could contribute to this event. Firstly, a short circuit may have occurred. The demolition cut could have created a direct short between the phase and neutral conductors, or between the phase and ground conductors. This sudden high current flow would cause both the branch and main breakers to trip. Secondly, a ground fault is another possibility. If the hot phase conductor came into contact with ground, it would create a path for current to flow to ground. The 20-amp branch breaker should trip in response to this ground fault. However, if the fault current is sufficiently high, it can also trip the upstream 400-amp main breaker. Thirdly, an overload condition might be the cause. Although less likely in this scenario, the demolition work could have inadvertently increased the load on the lighting circuit beyond its rated capacity. This sustained overload on the 20-amp branch breaker could have, in turn, stressed the main breaker and caused it to trip as well. Fourthly, a chain reaction could have occurred. The initial tripping of the branch breaker could have created a surge or momentary fault condition that overwhelmed the main breaker, leading to its subsequent trip. The 20-amp branch breaker is designed to protect the individual lighting circuit from overcurrents, whether caused by short circuits or overloads. Its primary function is to interrupt the circuit and prevent damage to the wiring and connected equipment. The 400-amp main breaker serves as the main overcurrent protection device for the entire mall electrical system. It is sized to handle the total anticipated load of the mall and to protect the system from major faults or overloads. The main breaker should be coordinated with the branch breakers. This means that the main breaker should be able to withstand the fault current that the branch breakers are designed to handle. If the main breaker trips at a lower fault current than the branch breakers, it could indicate a coordination problem, which could stem from various things. Firstly, inspect the demolition area thoroughly. Look for any exposed wires, damaged insulation, or signs of physical damage to the electrical components. Secondly, verify that the electrical system is properly grounded. A good ground connection is essential for the proper operation of ground fault protection devices and for overall electrical safety. Thirdly, calculate the total load on a lighting circuit to ensure it is within the 20-amp rating of the branch breaker. An excessive load can cause the breaker to trip even without a fault. Fourthly, test the circuit for ground faults using a ground fault circuit interrupter or multimeter. These tools can help identify the presence of unwanted current leakage to ground. Finally, consult with a qualified electrician to conduct a more comprehensive investigation. They have the expertise and equipment to diagnose the problem accurately and implement the necessary repairs. It is important to remember that working with electrical systems can be dangerous. It is always best to consult with a qualified electrician to ensure the safety of everyone involved. NEC Table 310.15. B16 provides ampacity ratings for conductors based on insulation type and temperature rating. Ensure that the conductors in the lighting circuit are properly sized for the 20-amp breaker. A conductor that is too small can overheat and create a fire hazard. If the neutral conductor is shared between multiple circuits, it may be overloaded. The NEC has specific rules for sizing neutral conductors in multi-wire branch circuits. Surge protection devices can help protect sensitive electronic equipment from voltage spikes and surges. These devices should be installed at the service entrance and at branch panels. Arc fault circuit interrupters are designed to detect arc faults, which are a common cause of electrical fires. These breakers should be installed in branch circuits that serve bedrooms and other areas where arc faults are more likely to occur. The electrical system should be inspected regularly to identify and correct any potential problems. A qualified electrician should perform the inspection. A short circuit typically involves a very high current flow, often many times the rating of the breaker. This high current causes the breaker to trip very quickly. A ground fault involves a current flow to ground, which is typically lower than a short circuit current. Ground fault circuit interrupters are designed to trip at very low current levels, typically 5 mA. An overload involves a current flow that is higher than the rating of the breaker, but not as high as a short circuit current. Overloads can cause the breaker to trip after a delay. The time it takes for a breaker to trip depends on the amount of overcurrent. The main breaker should be selectively coordinated with the branch breakers. This means that the branch breaker should trip before the main breaker in the event of a fault on a branch circuit. Selective coordination helps to prevent nuisance tripping of the main breaker. If the main breaker trips frequently, it could indicate a problem with the electrical system. The problem should be investigated and corrected as soon as possible. The electrical system should be properly maintained to ensure its safety and reliability. Proper maintenance includes regular inspections, testing, and repairs. The 20-amp breaker is likely a thermal-magnetic breaker. Thermal-magnetic breakers use a bimetallic strip to trip on overloads and an electromagnet to trip on short circuits. Electronic trip breakers use electronic components to detect overcurrents and trip the breaker. Electronic trip breakers are more accurate and provide better protection than thermal magnetic breakers. Molded case circuit breakers are typically used in branch circuits and feeders. Insulated case circuit breakers are typically used in main switchgear. The interrupting rating of a breaker is the maximum amount of current that the breaker can safely interrupt. The interrupting rating of the breaker should be greater than the available fault current at the breaker location. The available fault current is the amount of current that would flow in a short circuit at a given location. The available fault current can be calculated using engineering software or by using the point-to-point method. If the available fault current is greater than the interrupting rating of the breaker, a breaker could fail to interrupt the fault, which could result in serious damage or injury. The impedance of the circuit conductors can affect the available fault current. The longer the circuit conductors, the higher the impedance, and the lower the available fault current. Transformers can also affect the available fault current. The impedance of the transformer will limit the amount of fault current that can flow. Generators can also contribute to the available fault current. The amount of fault current that a generator can contribute depends on the size and type of generator. The available fault current should be calculated at each breaker location in the electrical system. This information is used to select breakers with the appropriate interrupting rating. The electrical system should be designed and installed in accordance with the National Electrical Code. The NEC provides requirements for the safe installation of electrical systems. The electrical system should be inspected by a qualified electrical inspector to ensure that it complies with the NEC. The electrical inspector will look for potential hazards and ensure that the system is installed correctly. If any problems are found during the inspection, they should be corrected before the system is put into service. The electrical system should be properly grounded to protect against electric shock. Grounding provides a low impedance path for fault current to flow back to the source, which causes the breaker to trip. The grounding system should be installed in accordance with the NEC. The grounding system should be tested regularly to ensure that it is working properly. Surge protection devices can help protect sensitive electronic equipment from voltage spikes and surges. These devices should be installed at the service entrance and the branch panels. Arc fault circuit interrupters are designed to detect arc faults, which are a common cause of electrical fires. These breakers should be installed in branch circuits that serve bedrooms and other areas where arc faults are more likely to occur. The electrical system should be inspected regularly to identify and correct any potential problems. A qualified electrician should perform the inspection. If the demolition work involved cutting into the grounded neutral conductor, this could also cause the main breaker to trip. This is because the grounded conductor provides the return path for current, and if it is interrupted, the current may find an alternate path back to the source, which could trip the main breaker. If the demolition work involved cutting into a conduit that contained multiple circuits, this could also cause the main breaker to trip. This is because the cutting could damage the insulation on the conductors, which could lead to a short circuit or ground fault. If the demolition work involved using heavy equipment, the equipment could have damaged the electrical system. This could include damaging underground cables or overhead lines. If the electrical system was not properly energized before the demolition work began, this could have caused the accident. It is important to always energize electrical systems before working on them. If the electrical system was not properly maintained, this could have contributed to the accident. Proper maintenance includes regular inspections, testing, and repairs. If the electrical system was not properly designed, this could have contributed to the accident. The electrical system should be designed by a qualified electrical engineer. If the electrical system was not properly installed, this could have contributed to the accident. The electrical system should be installed by a qualified electrical contractor. If the electrical system was not properly inspected, this could have contributed to the accident. The electrical system should be inspected by a qualified electrical inspector. If the electrical system was not properly operated, this could have contributed to the accident. The electrical system should be operated by qualified personnel. If the electrical system was not properly maintained, this could have contributed to the accident. The electrical system should be maintained by qualified personnel. If the electrical system was not properly designed, this could have contributed to the accident. The electrical system should be designed by qualified personnel.